Bismillahirrahmanirrahim. Now, in this lecture, we understand what is Fleming left-hand rule and Fleming right-hand rule. Fleming was a scientist. He invent right-hand rule for generators. Fleming right-hand rule. RHR. Fleming right-hand rule used for generators and used for the, actually there are three parameters, right? X, Y, Z. We have three parameters, that is Fleming right rule is E, V, B. E induced voltage, V velocity of the conductor, B magnetic field, right? All these parameters are perpendicular to each other, like X, Y, Z axis. All these parameters are perpendicular, that is E, V, B. V is velocity, E is voltage induced, B is magnetic field, right? So let's consider a linear motion conductor, that is a conductor in which the motion, the conductor, either it moves right to left or left to right, bar or a conductor, right? Same thing, the conductor. So let's suppose it moves towards right? It's a linear motion, so it moves towards right, and the magnetic field is cross meet into the page, right? Cross meet into the page. If there are dots, dot mean out of the page, because magnetic field may be into the page, magnetic field may be out of the page, right? So consider the velocity of the conductors like this. This is the velocity of conductor. This is a magnetic field that is into the page, to the page, right? So what is the direction of voltage induced? That is, what is the direction of current, or what is the polarity of voltage induced in this conductor using your right hand, right? So put your fingers like this, your three fingers, you put your fingers like this. Your middle finger will show you E, that is induced voltage. Your forefinger shows to you the magnetic field, and the thumb will show you the velocity of the conductor. C, E, B, V, right? E, voltage induced, B, magnetic field, the index finger, thumb, the velocity of the conductor. For this case, for this particular case, because the magnetic field is into the page, right? So you take your right hand like this. See, your right hand. Yeah, the thumb will show you the velocity of the conductor, that is from left to right. See, velocity is like this, right? This is magnetic field, index finger. It is into the page, right? Into the page. So the voltage induced is positive, is because your middle finger comes like this. So voltage induced is positive and negative. The induced voltage in this conductor is, or the current flow like this, right? The current flow from down to up, the current flow or induced voltage, right? So this is right hand rule, right? Now we change the velocity of this conductor. See what happens. We change the velocity. You have two choices, right? Either you change the velocity of the conductor, or you change the magnetic field polarity, right? Anyhow, if you change anything, you will get the voltage induced in opposite direction, right? But change one parameter. Either you change the velocity or you change the magnetic field, because induced voltage is equals to VBL, right? Remember, induced voltage is equals to VBL, velocity of the conductor, magnetic field, length of the conductor, right? Induced voltage is this. So now in this case, you change the velocity of the conductor. Now let's suppose conductor moves in opposite direction, right? Conductor moves in opposite direction. Again, you put your right hand like this. See, before it was like velocity was here, but now see, the velocity direction is opposite. So you just alter the finger of velocity, that is thumb. You need to alter it, right? You see, you alter the thumb. Again, your magnetic field in, but your middle finger go downward. So positive of induced voltage comes over here, right? See how it applies. It applies like this. It applies like this, right? The velocity, the thumb is velocity, right? The index finger is again into the page, and the middle finger is downward, right? Downward means the tip of middle finger shows to you positive induced voltage in the conductor. So this how the right hand rule apply in the generators to find the polarity of induced voltage or the direction of current flow. I hope you understand. Now Fleming left hand rule for motors, right? LHR, Fleming left hand rule, generally used for motors for the direction of rotation, to find the direction of rotation of the motor. You must know in which direction the motor will rotate. Either it rotates in clockwise or it rotates in counterclockwise direction. So again, take the example of the bar, that is conductor. This is the bar, conductor. Now force induced is BIL, right? BIL, magnetic field, current, length of the conductor, right? Remember this, the induced force is like this, right? So again, the conductor, the magnetic field is into the page, right? And the current flow in the conductor, for example, is like this. The current flow from top to bottom. And again, you have three parameters, that is, you have three parameters. FBI, right? FBI, force induced, right? The direction of rotation, magnetic field, I means current, right? Now place your left hand, right? Place your left hand, and you see you have three fingers. So now you have FBI. On your thumb, on your thumb, you have F. On your index finger, you have magnetic field. On your middle finger is current, right? F, that thumb, B, index finger, I, current, middle finger, right? So put your left hand and apply over here on this conductor. See, magnetic field is into the page, the current is downward, so you apply like this. See, your middle finger is downward, your index finger is into the page, your thumb is from right to left. So the force induced in this conductor, the force induced direction in this conductor is like this. See, your thumb will show the induced. See, the current is downward, see the middle finger, and the magnetic field is into the page, see the index finger is into the page, right? And thumb will show you the induced force direction, that is like this. Now consider the other case, that is if the direction of current flow is reverse in the conductor, in the bar, it reverse. Now the current flow is like this. See, the current flow, that is I, is upward now. So how the force induced will be in this case? How the force induced? Now again, you put your left hand, before it was like this. See, you alter that finger in which the current changes. The current is now upward. See, you just change this. See, this upward, right? So what your thumb is showing? Yes, your thumb is showing that force induced will be in this direction if the current is upward. See, if the current is upward, the force, see, the middle finger is upward, the index finger is again into the page, and the thumb will show you the induced force direction of the conductor, that is like this. So by altering the current, the induced force, that is direction of the bar, changes actually. So how the motor direction changes actually, when you when you change the supply direction of the motor, that is when you give the supply positive, negative to the motor, it will run in a certain direction. And when you take alter that supply, that is negative, positive, then the motor direction will opposite, right? So we justify from this left hand rule. I hope you understand. Now curl the fingers rule, that is curl the right hand finger, curl the finger, again RHR, to find the magnetic field direction, magnetic field, that is magnetic field direction, that is magnetic north pole, right? Because when we say that magnetic field polarities, that means the magnetic north and magnetic south pole, right? So magnetic north and south are similar to EMF polarities, like positive and negative. Positive is north, negative is south. Magnetic field lines flow from north pole to south pole. So consider consider a coil, that is coil in which the current flows. Consider a coil, right? A coil, current flows, right? This is at the terminals, right? And in the winding, the current flow, like, see, if you remember the ladders, the current flow like top to bottom. Current like comes like this, top to bottom. See, current come in a coil and it flows like this, from top to bottom, from top to bottom. So put your right hand and curl your fingers in the direction of current flow. The thumb will point out the magnetic field polarity, right? So when you insert your right hand and curl your fingers in the direction of current flow, your thumb will point out the magnetic field direction, right? So in this case, the magnetic field, the magnetic field comes top, the current goes down. See, this is B, this is magnetic field, and this is current. Current go downwards, magnetic field go upwards. The example is same as a car. If car go forward, the smoke of the car goes backward, right? Current go downward, magnetic field direction is upward, means the magnetic field north pole is over here and south pole is over here. Now reverse the current direction. Now reverse the current direction. Now you may consider that you give the supply current from here and you take the return current from here, right? Opposite. Now current enters from bottom, and bottom it goes to top. See, it's a round ladders go from bottom to top. So again, the direction of current flow is like, or in other words, the direction of current flow the direction of current flow is like, comes so in this case you again use your right hand and you put your right hand and you curl the fingers in the direction of current flow. This time the direction of current flow is like this. When you curl the fingers, your thumb will point out downwards. See, your thumb will point out downwards. So in this case, the current is from bottom to top, that is current. The magnetic field is from bottom to top. So magnetic field, by curl the fingers, you get the magnetic field, right? Another example, if you want to another example, if the magnetic field direction is given to you, for example, this direction, magnetic field direction is given to you, then you curl the fingers, you in the direction of magnetic field, the thumb will point the current direction, right? This is a conductor. When you curl the fingers in the in direction of magnetic field, the thumb will point out the current flow. The current flow is upward. See, the magnetic field is like this. Or let's another example. Now take this example. The magnetic field in this the magnetic field direction was actually clockwise. Now anti-clockwise. So when you use your right hand and you curl the fingers in the direction of magnetic field, you will get the current direction, that is downward. I will give the PPT of these these explanations also. That is right hand rule, left hand rule, curl the fingers rule. I will give you PPT, and from PPT you will well understand. I hope you understand from this also. Thank you. Bismillahirrahmanirrahim. Another way to find the direction of voltage induce in generator, we know that induced voltage is V cross B dot L. Velocity, magnetic field. L means length of conductor. So actually, it's a cross polarity of voltage and magnetic field. So first vector, that is voltage, rotates towards second vector. So if you put your right hand first vector, that is velocity, it rotates towards magnetic field. If you put your fingers first, that is velocity rotates towards magnetic field. See, your thumb will point in, right? The thumb is into the page, right? The positive induced voltage is into the page, or current flow is inward, right? And in this figure, see, the velocity is downward, the magnetic field vector is over here. You put your right hand and and first vector rotates towards second vector, that is velocity towards magnetic field. You just curl the fingers, your thumb will point out, right? The current is out, or the voltage induced positive polarity is out. So see, the first vector rotates towards second vector. You put your and rotate. See, your thumb will point the direction of induced voltage or direction of current, right? Similarly, in motors, induced forces B, magnetic field, times current times length of the conductor. So put your left hand, because it's a left hand rule, right? When your current, the first vector rotates towards second vector, that is current towards magnetic field. So see, when current is upward, your magnetic field is like this, right? When current is downward, see, in this case it was outward, and in this case it was inward, right? Inward, in. So I hope you understand. This is very clear understanding for the direction of voltage induced or current pass, the force induced direction, right? Or the direction of motion of the motor. That's why when we give supply motor to positive negative, it rotates in certain direction, and when we switch that supply to negative or negative to positive, then it will rotates in opposite direction. Similarly, the generator case, when we change the velocity of the generator prime mover, that is input, the generator generates a voltage that is positive negative, and when the velocity of the generator changes, the generator voltage also switches, that is negative positive. So that's why it switches all the times. In AC, we have a study rotating magnetic field, and rotating I forgot one thing to tell you. See, when this cycles come, magnetic field, positive cycle of magnetic flux comes, then it forms north pole, and when negative cycle of magnetic flux comes, it forms south pole. So the poles are switching, actually the poles are switching, north south, north south. The positive supply, the pole becomes north, then negative supply, the pole becomes south. So in this way, rotating magnetic field switches its position, north south, north south, right? North south, north south. I hope you understand. Bismillahirrahmanirrahim. This is another representation for velocity, means generator and motor, right? First of all, come towards the generator. If you place your fingers, the right hand fingers, thumb will show you the direction of velocity. The index finger will show you the magnetic lines direction, and middle finger will show the polarity of voltage induced. So in this condition, see, the velocity is upward. See this conductor, the velocity is upward, the magnetic field is from right to left. This is north pole, this is south pole, so magnetic field is from right to left. So this is magnetic field, and this is velocity of the conductor. So the middle finger, it points in, right? So the positive of the EMF induced is into the conductor, actually. And if you alter the velocity, for example like this, see, you alter the velocity alters, right? When you alter the velocity, your middle finger comes out, that is the positive of the induced voltage is at terminals out, right? Here terminals in and here terminals out, because velocity is changed. See the velocity direction. Similarly, the rule for the motor, see, in these conductors which are under the influence of south pole, similarly is the case for the motor. See, this is north pole, this is south pole, this one is north, this one is south. Magnetic field lines are like this. So see the conductors which are, these conductors are influence of north pole, these conductors are influence under the south pole. The current on these conductors upward, and the current in these conductors are downward, right? You know the coil offers the current, that is the coil which offers the current. The one way the current will go into the coil, the one way the current out of the coil, right? See the current going and current leaving. So what, right? So if you place your left hand fingers, your thumb will point out the direction of current, the index finger points out the magnetic field, and the middle finger will tell you the force induced, that is force induced in that conductor, that is motion of the conductor. So in this case the current is upward, the middle finger, and the force induced is, see, current is upward, the force induced is like this, means the force, it will rotate in like this direction, right? If the current is upward, if the current is downward, then the rotation becomes like this, right? So see, the current is upward, the current is downward. See, the current is upward, the current is upward, okay, the current is downward. So this middle finger, this will point out the direction of force induced, right? So force induced changes when the direction of current changes. I hope you understand. Now consider rotating conductor, right? Before we take the example of linear conductor, that is linear motion. Now in rotational motion, we see how the we can find the direction of induced EMF or direction of rotation of a conductor. For example, this is a rotor. This is rotor, and it is rotating in a, for example, counterclockwise direction. It rotates in a counterclockwise direction. So we want to know the direction of rotation of this rotor, whether it rotates in counterclockwise or whether it rotates in a clockwise direction. For this, we need to consider a coil, a coil, and because we are giving supply to the coil, for example, positive, negative, the current will flow like this. The current will go in the coil and coming out from this, right? So when coil is placed in these two slots of the rotor, so in this rotor slot the current is upward, in this rotor slot current is downward, right? So you apply your left hand rule for the direction of rotation of this rotor, right? Again, consider the magnetic field line, that is, for example, this one is north pole, this one is south poles. The magnetic field lines are like this, right? So for this you have to place your left hand rule for the direction of rotation. The current is upward, you apply like this, right? See, these are the magnetic field lines, okay. What FBI, right? f FBI, right? So if you consider this coil is placed, for example, like this is coil, right? So the current, okay, for example, the current go here and the return current is from here, right? The current go and current returns from here. So you apply your left hand, right? And this is magnetic field, this one is current, okay. So current is inward and current is downward, right? For example, this current, if you place the coil, the current goes into the conductor, and from other side current goes out of the conductor, right? Current in, current out, current in, current out, current in, current out. So this one is current in, right? and cross. Now this one is current out. This one is current out. So when you place your right hand rule and current in, it will shows to you like this. The fingers are like this. See, your thumb point out the downwards. So the direction of rotation is downward, right? The direction of rotation is, see, the direction of rotation is magnetic field. Current is in the middle finger. Current, see the middle finger. Current is in. The magnetic field is like this. Thumb will point out the direction of rotation, and thumb is downward. So direction of rotation is like this. Okay. When you put this it out of current, right? You just alter the finger. See, out. Magnetic field remains same, right? Current is out. So the thumb will show you the direction of rotation, that is upward. See, the direction of rotation is upward. See, like this. I hope you understand. The direction is, see my thumb show upwards, and upward means the direction of rotation is like this. The index finger show the magnetic field lines. Magnetic field lines are from right to left, north to south, and the middle finger shows the current is from out of the conductor. So the conductor moves like this. See, the coil, it has certain direction of current, and under the influence of north pole it rotates downward, and when it is in the influence of south pole, it rotates up. So in this way the rotor rotates. See, rotor rotates. One coil of side offer inward current, one side coil outward currents, right? Because of current reverse direction, the rotation is reverse. I hope you understand. Now consider the current, the generator case, in which you have to apply a right hand rule on rotational motion, right? Because previously it was motor, we give supply to the coil. Now we rotate this coil through prime mover, right? So either we rotate it in a counterclockwise direction or in a clockwise direction. For example, in this case, we are rotating our rotor in a counterclockwise direction. See, this direction is counterclockwise, right? So we know that our three fingers, that is EBV. We have three fingers, right? We have three fingers, EBV. E induced voltage, right? B magnetic field, V velocity of the conductor. So velocity of conductor and magnetic field are known to us. This finger will tell us positive induce in the conductor or positive induce out the conductor, right? So let's start. So consider this case. See, the velocity of the conductor is upward. The magnetic field lines are from north to south. See, the magnetic field lines are from north to south. That is in same direction in the motor also. The magnetic field lines, and see, you place your right hand like this. These are magnetic field lines. This finger shows you magnetic field lines. This one velocity of the conductor. The middle finger is into, right? See, positive is into the page. Positive appears like this. The EMF polarity is positive, right? And when you come over here, see, it moves from here. See, the rotor go up. The rotor go up, right? And here rotor go down, right? So when you come here, you just alter the finger, right? See, rotor come down. Again the index finger middle, that is magnetic field same. The rotor velocity changes, right? So your middle finger shows out. So positive is out, right? So that's why the polarity in the rotational motion alters actually. Every time the rotor conductor alters, its polarity alters. When the rotor conductors are in the influence of south pole, and when the rotor conductors are in the influence of north pole, the voltage generated is alter always. That means positive, negative, negative, positive. You see, the polarities alter in this way. So I hope you understand. This is actual motion of the conductor, actual generation, in which you found the polarity of the generated voltage. So that's why your voltage alter all the time.